Imagine for a moment that you are standing outside on a clear night. The air is still. The sky above you is dark enough that the stars are visible, not just the brightest ones, but the deeper ones too, the ones that require a moment of stillness and patient looking before they reveal themselves. The Milky Way, perhaps, arching overhead in its pale and ancient river of light. You look up, and somewhere among those countless points of light, there is a star unremarkable in appearance, indistinguishable from its neighbors around which orbits a small, rocky world. A world with an atmosphere. A world where something has been happening for a very long time. And tonight, a telescope drifting quietly in space 1.5 million kilometers from Earth has turned its golden mirrors toward the light of that distant star. It has collected photons that pass through the atmosphere of that world. It has spread those photons into a spectrum and read the chemical signatures written there. What it found has been analyzed, peer-reviewed, debated, verified. And what it found has changed everything. Tonight, we explore what it would truly mean, in the deepest sense, if James Webb were to detect the signs of a civilization on a newly discovered world. We will move slowly and carefully through the science of how such a detection would work, what it would and would not tell us, how astronomers would respond, and what the implications would be for our understanding of the cosmos and our place within it. This is a story that has not yet been told, but it is a story that the universe may be preparing to tell. And the framework for understanding it, the science, the mathematics, the philosophical depth of what such a discovery would mean, is real, established, and worth exploring with the patience and care it deserves. We have the whole night ahead of us. There is no hurry. There never is. As we begin our journey tonight, let us understand how it is even possible for a telescope to detect anything about the atmosphere of a planet orbiting a star hundreds of light years away. Because the method itself is one of the most elegant pieces of scientific ingenuity in the history of astronomy. The technique is called transit spectroscopy, and it works as follows. When a planet passes in front of its host star, an event called a transit, it blocks a small fraction of the star's light. For a planet the size of Earth orbiting a sun-like star, that fraction is roughly 1 part in 10,000, a tiny dimming, measurable but subtle. But here is where elegance enters. During a transit, a small amount of the star's light does not pass through empty space between star and telescope. Instead, it passes through the edge of the planet's atmosphere, the thin ring of gas surrounding the planetary disk. As that light travels through the atmosphere, different molecules in the atmosphere absorb different specific wavelengths. Each molecule has a characteristic fingerprint, a pattern of wavelengths it absorbs, that is as unique as a signature. By carefully subtracting the star's spectrum observed during the transit from the star's spectrum observed outside the transit, astronomers can isolate the contribution of the planetary atmosphere. What molecules are present, in what concentrations, at what altitudes. The precision required for this is extraordinary. The signals are vanishingly faint. The wavelength differences between molecular absorption features are measured in fractions of a nanometer, and the observations must be made across multiple transits, accumulated over months or years, before the signal rises above the noise with statistical confidence. James Webb was designed from its earliest specifications to perform exactly this kind of observation with a precision no previous telescope could match. Its large mirror area, its infrared sensitivity, its stability in the thermal environment of the L2 point. All of these were chosen, in part, to enable the reading of planetary atmospheres across interstellar distances. The telescope is, in a very real sense, a chemical detector pointed at other worlds. Let us explore the concept of biosignatures, the chemical signatures that might indicate the presence of life on a distant world, because understanding them is essential to understanding what a civilization detection would mean. A biosignature is any chemical or physical feature of a planet's atmosphere or surface that can best be explained by the presence of biological processes. The concept is rooted in the principle that life, wherever it exists and whatever form it takes, must interact with its environment, consuming certain chemicals, producing others, leaving a measurable imprint on the world it inhabits. On Earth, the most discussed potential biosignature is oxygen. Our atmosphere contains approximately 21% molecular oxygen, a highly reactive gas that, in the absence of continuous biological replenishment, would react with surface rocks and organic matter and disappear within geological timescales. The oxygen in Earth's atmosphere is there because photosynthesis continuously produces it. Without life, it would be gone within a few million years. An atmosphere containing large amounts of free oxygen, detected on a rocky planet in the habitable zone of its star, would be a compelling, though not definitive, indicator of biological processes. Other potential biosignatures include methane, which, in combination with oxygen, is a particularly interesting pair, since the two react and destroy each other. Finding both simultaneously in a planetary atmosphere implies a continuous source of both, a source that, on a world with appropriate conditions, most naturally points toward biology. Nitrous oxide produced by microbial processes on Earth has been identified as another potential biosignature. Dimethyl sulfide, produced in Earth's oceans by phytoplankton, leaves a distinctive spectral signature. But what of civilization? What chemical signatures might indicate not merely life, but intelligent, technological life? The answer to that question is where our story tonight becomes most extraordinary. As we continue our journey, let us explore the concept that takes us beyond biosignatures into the territory relevant to tonight's scenario, the idea of technosignatures. A technosignature is any observable feature of a planet, a star, or a broader astronomical system that can best be explained by the presence of a technologically capable civilization. It is the category of evidence that would indicate not just life, but intelligent, tool-using, energy-consuming, world-altering life. The most discussed technosignature in the context of atmospheric chemistry is a molecule that does not occur naturally in any environment. We know of a molecule that can only be produced through industrial chemistry or technological processes. Chlorofluorocarbons, or CFCs, are one such molecule. On Earth, CFCs were produced industrially as refrigerants and aerosol propellants. They do not occur naturally. They are persistent in the atmosphere, surviving for decades before being broken down by ultraviolet radiation. And they have a distinctive spectral signature detectable in the mid-infrared portion of the electromagnetic spectrum. If James Webb were to detect chlorofluorocarbons, or similar industrially produced molecules with no natural production pathway in the atmosphere of a rocky planet, that detection would be difficult to explain by any natural process. It would point strongly, perhaps overwhelmingly, toward industrial activity. Nitrogen dioxide in high concentrations associated on Earth with combustion processes and industrial activity is another potential technosignature. So are certain isotopic ratios of elements that might be altered by nuclear processes. The scientific community has been increasingly serious about technosignature research. NASA workshops, peer-reviewed papers, and dedicated research programs have been devoted to understanding which technosignatures are detectable with current or near-future telescopes and what they would mean if detected. It is not fringe science. It is careful, rigorous, and important science. Consider how such a discovery might actually unfold the sequence of observations and analyses that would lead from an initial anomaly to a confirmed extraordinary result. It would likely begin not with a dramatic announcement, but with a quiet anomaly in a data file. A planet, let us imagine it as a rocky world approximately 1.2 times the size of Earth, orbiting a K-type star somewhat cooler and slightly smaller than our Sun, at a distance placing it comfortably within the star's habitable zone. A planet whose existence had been catalogued by previous surveys, whose orbital period had been measured, whose host star had been characterized. A routine transit observation with Webb would produce a spectrum. That spectrum would be analyzed by automated pipelines that search for the signatures of known atmospheric molecules. Most such spectra yield interesting, but not extraordinary results, hints of water vapor, perhaps carbon dioxide, the signatures of a plausible but unremarkable atmospheric chemistry. But in this particular spectrum, something unexpected appears. A set of absorption features at wavelengths that do not correspond to any molecule expected from geological or biological processes. A pattern that, when compared against databases of molecular spectra, matches closely to molecules associated with industrial chemistry. The automated pipeline would flag it. A researcher would look more carefully. More observations would be scheduled. Additional transits, additional accumulation of photon counts, additional refinement of the signal. And as the data accumulated, the anomaly would not go away. It would grow clearer, more defined, more unmistakably extraordinary. This is how science works, not in a single dramatic moment, but in the slow accumulation of evidence, the gradual building of confidence, the careful ruling out of alternative explanations. And in this imagined case, the alternatives would run out. As we continue, let us explore how the scientific community would actually respond to such a detection, because the process of verification is as important as the detection itself, and it reveals something profound about how science operates at its best. The first response would be skepticism, not dismissal, but rigorous, principled skepticism. The history of science is full of anomalous signals that turned out to have mundane explanations. Systematic errors in instrument calibration, contamination of spectra by stellar features, statistical fluctuations that appeared significant but were not. The history of the search for extraterrestrial intelligence, in particular, contains several instances of promising signals that ultimately proved to have prosaic origins. So the initial response to an apparent technosignature detection would be a methodical search for every possible alternative explanation. Could the signal be explained by an instrumental artifact, some quirk of the detector or the optical system? Could it be a feature of the star's own spectrum, imperfectly subtracted? Could it be produced by some unusual but natural atmospheric chemistry not previously encountered? These questions would be pursued thoroughly and without prejudice. The scientists involved would want to be wrong, not because they would not welcome the discovery, but because the discipline of trying to disprove a result before accepting it is what makes science trustworthy. Multiple independent groups would be given access to the raw data to perform their own analyses. Different methodological approaches would be applied. Different software pipelines, different assumptions, different models. If the signal were real, it should survive all of these tests. Observations would be repeated not just with Webb, but with every available instrument capable of contributing. Ground-based telescopes with relevant capabilities. Other space telescopes. Any observatory that could contribute additional data on the target system would be mobilized. And throughout this process, which might take months or years, the results would be closely held. Not to suppress information, but to ensure that when a result was released to the world, it would be the most carefully verified claim in the history of science. Let us sit with the question of what standard of evidence would be required before the scientific community would accept such a detection as genuine, because the standard itself reveals something important about the relationship between science and extraordinary claims. The principle most often invoked in this context is one associated with the astronomer Carl Sagan. Extraordinary claims require extraordinary evidence. It is a principle rooted in Bayesian reasoning, the logical framework for updating beliefs in light of evidence. Before any observation is made, our prior probability for the existence of a detectable technological civilization on any given planet is extremely low. There is exactly one confirmed technological civilization in the universe, our own, and we have no statistical basis for knowing how common such civilizations are. Our prior is, necessarily, very low. When a signal is detected, the posterior probability, our updated probability, in light of the evidence, depends on both the strength of the evidence and the prior probability. Because the prior is so low, the evidence required to raise the posterior probability to the level of confident acceptance must be correspondingly strong. What would that evidence look like? It would need to rule out every natural explanation for the observed signal with extremely high confidence. It would need to be reproduced across multiple independent instruments and analyses. It would need to be consistent with multiple transits observed over time, not a single observation, but a pattern that persists and strengthens. Ideally, it would involve not just one molecular signature, but multiple signatures that, taken together, form a coherent picture impossible to explain naturally. The combination of unexpected molecules at concentrations implying active production, combined with perhaps other indicators, unusual albedo patterns, distinctive thermal emission signatures, would build a case that no single piece of evidence alone could make. The standard would be high, appropriately high, and meeting that standard would be one of the greatest achievements in the history of science. As we journey deeper tonight, let us carefully explore what a confirmed technosignature detection would actually tell us, and, equally important, what it would not tell us. What it would tell us, with high confidence, is that a planet exists on which some process, almost certainly technological, is producing molecules of a kind not generated naturally. It would tell us that those molecules are present in the planet's atmosphere in concentrations consistent with ongoing production rather than a one-time event. It would tell us that the star system in question hosts a world where something is happening that requires explanation beyond the known processes of geology, atmospheric chemistry, and biology. Beyond that, the inferential path becomes longer and more uncertain. We would not know, from atmospheric chemistry alone, the nature of the civilization. We would not know whether it is young or old. We would not know its level of technological development. We would not know whether it is aware of us or has any concept of interstellar observation. We would not know whether it is currently thriving or in decline. The light we observe left the planet years, decades, or centuries ago, depending on its distance. The civilization whose chemical signature we are reading might have changed dramatically, collapsed, or expanded beyond recognition in the time it took its atmospheric fingerprint to reach us. We would not know whether the beings responsible for the signatures are biological like us or something else entirely. We would not know whether their civilization emerged recently or has persisted for millions of years. The detection would be, in this sense, the opening of a conversation rather than the delivery of a message. It would tell us the most important thing, that we are not alone. But almost every other question about who and what and why would remain, for now, unanswered. A single extraordinary fact, surrounded by infinite mystery. Consider the profound significance of distance in this scenario, because the distance to the hypothetical planet is not merely a practical obstacle, it is a philosophical dimension of the discovery. For a planet to be detectable by James Webb through transit spectroscopy, it needs to be in a system relatively close to Earth on cosmic scales within a few hundred to perhaps a few thousand light-years. At greater distances, the stellar light becomes too faint and the atmospheric signal too dilute for current technology to extract. Let us imagine the planet is 100 light-years away, a modest distance by galactic standards nearby, in the scheme of the Milky Way's 100,000 light-year breadth. 100 light-years means that the light we are analyzing left the planet 100 years ago. The atmospheric chemistry we are reading is a century-old snapshot. The civilization whose industrial molecules we are detecting, if they still exist, has had 100 years of additional history since that light was emitted. And any signal we were to send toward that world today traveling at the speed of light would not arrive for another 100 years. A response, if one were sent immediately upon receipt, would not reach us for 200 years from now. 200 years. 8 generations of human beings. More time than has passed since the Industrial Revolution. This is not a conversation in any ordinary sense. It is an exchange of messages across a gulf of time that dwarfs individual human lives. Whatever we learn from the detection, and whatever dialogue might eventually follow, it would unfold on a timescale that belongs to civilizations rather than individuals. There is something both humbling and magnificent in that. The discovery would belong not to any person alive today, but to humanity as a whole, to the long, slow arc of our collective story. As we continue our exploration, let us consider what a confirmed detection of a technological civilization would mean for one of the deepest unresolved questions in science, the Fermi paradox. The Fermi paradox, as we have explored in other journeys, is the apparent contradiction between the large number of stars and potentially habitable planets in the galaxy and the complete absence of any confirmed evidence of technological civilization beyond Earth. The universe is old. It is vast. Stars like the Sun have been forming for 10 billion years. If technological civilizations arise with any reasonable frequency, some of them should have had billions of years to develop, expand, and make their presence known. And yet we have heard nothing, seen nothing, found nothing. The detection of even a single other civilization, even one that is merely producing industrial chemicals on a rocky planet 100 light-years away, would transform this situation completely. Before the detection, the number of confirmed technological civilizations in the observable universe is exactly one us. From one data point, no statistical inference is possible. We cannot know whether we are typical or exceptional, early or late, common or vanishingly rare. After a confirmed second detection, we have 2 data points. That is still a small sample, but the implications are profound. 2 confirmed civilizations, both in the Milky Way, separated by 100 light-years, would suggest, through a conservative statistical argument, that the galaxy contains many more, possibly millions. The silence of the Fermi paradox would demand a different explanation, not that civilizations are extraordinarily rare, but that interstellar communication or expansion is harder or less motivated than we assumed. One detection would not answer all the questions the Fermi paradox raises, but it would dissolve its most fundamental premise, the premise that we are alone. And in dissolving that premise, it would change the entire context of human self-understanding. Let us revisit the Drake equation, the famous framework for estimating the number of detectable civilizations in the galaxy, and see how a single confirmed detection would transform its most uncertain parameters. Frank Drake formulated his equation in 1961 as a way of organizing the problem of estimating the number of communicating civilizations in the Milky Way. The equation multiplies together a series of factors: the rate of star formation, the fraction of stars with planets, the fraction of those planets that are habitable, the fraction where life arises, the fraction where intelligence develops, the fraction where technology arises, and the average lifetime of a technological civilization. The fraction, the first few factors, star formation rates, planetary occurrence rates, are now known with reasonable precision from decades of astronomical survey. We know that most stars have planets. We know that rocky planets in habitable zones are common. These factors are not the source of our uncertainty. The uncertainty lives in the later terms, particularly in the fraction of habitable worlds where life arises, the fraction where intelligence emerges, and the average lifetime of a technological civilization. These are the terms that range, in different scientists' estimates, from near certainty to near impossibility. They are the terms where genuine, profound ignorance lives. A single, confirmed detection of a second civilization would provide, for the first time, an empirical constraint on the combined effect of those uncertain factors. If there is another civilization within 100 light-years of Earth, given the stellar density of the galaxy in our neighborhood, that implies that the product of all those uncertain factors is not vanishingly small. Life, intelligence, and technology must arise with some meaningful frequency. The detection would not give us a precise number, but it would tell us that the number is not nearly 0. It would tell us that the universe is, in this most important sense, inhabited. As we move into the more contemplative chapters of our journey tonight, let us allow ourselves to wonder carefully and scientifically about the nature of a civilization detectable by atmospheric chemistry from 100 light-years away. The fact that its atmospheric chemistry is detectable implies several things. First, it implies that the civilization has reached at least an early industrial level of technological development. The production of atmospheric trace gases, in quantities detectable from 100 light-years away, requires planetary-scale industrial activity, or its equivalent. This is not a pre-industrial civilization. It is a civilization that has learned to use energy and chemistry at a significant scale. Second, the specific signatures matter. Chlorofluorocarbons, for instance, One of the molecules, discussed as a potential technosignature, were produced on Earth during a specific period of industrial development, roughly the mid-20th century. They are being phased out through international agreement because of their effect on the ozone layer. A civilization producing CFCs in detectable quantities might be, in an early industrial phase, analogous, perhaps, to Earth in the latter half of the 20th century. Or the molecules might be something different, industrially produced compounds with no natural pathway, but not necessarily the same as Earth's industrial chemistry. The specific compounds would shape our inference about the nature of the civilization. Third, the detection tells us nothing directly about the civilization's social organization, its level of awareness, its history, or its trajectory. A civilization might be flourishing and expanding. It might be in decline. It might be in a period of transition, moving away from the industrial processes that produce the detected signatures towards something cleaner and less chemically visible. We would be reading one page of a very long book, written in a language we only partially understand, from a distance of 100 light years. The wonder of that should not be lost in the desire for certainty. Let us explore the Kardashev scale, a framework for classifying civilizations by their energy use, and consider where a civilization detectable through atmospheric chemistry might fall within it. In 1964, Soviet astronomer Nikolai Kardashev proposed a classification system for civilizations based on their capacity to harness and use energy. A Type 1 civilization uses the full energy resources of its home planet. A Type 2 civilization harnesses the full energy output of its home star. A Type 3 civilization harnesses the energy of its entire galaxy. By this scale, human civilization today is approximately Type 0.73. We use a significant fraction of Earth's accessible energy resources, but are nowhere near the Type 1 threshold of complete planetary energy utilization. A civilization producing detectable atmospheric signatures through industrial processes is, almost by definition, a Type 1 civilization or approaching it. Industrial civilization requires planetary-scale energy use and planetary-scale chemical production. But here is something worth noting. As civilizations advance in the theoretical models that have been explored by physicists and futurists, they may become less, not more, visible in certain ways. A Type 2 civilization, harvesting a significant fraction of its star's energy through megastructures, would produce distinctive infrared signatures, the waste heat of those structures. But it might produce fewer dirty industrial atmospheric signatures if it had moved beyond the chemical industry that marks early technological development. A Type 3 civilization, if such things exist, might be so advanced, so efficient, and so far beyond the energy sources visible to us that its presence is invisible to our current instruments entirely. The civilizations most visible to us, through atmospheric chemistry, through the crude but detectable signature of industrial molecules, may be the young ones. The civilizations in the early phases of their technological development, the civilizations most like us. In detecting such a civilization, we might be seeing our own reflection across the gulf of space. As we continue our journey, let us contemplate how humanity, as a civilization, as a species, might receive such an announcement. The history of major scientific announcements suggests that the initial response would be varied, contested, and in some ways chaotic. Spectacular claims about extraterrestrial life have been made before the ALH 84001 Martian meteorite in 1996, which some scientists claimed showed signs of ancient microbial life, generated enormous initial excitement, followed by years of scientific debate that ultimately concluded the evidence was insufficient. False alarms and premature announcements have shaped public and scientific expectations. A confirmed technosignature detection announced through the proper scientific channels, with full data disclosure, peer review, and independent verification would be different. It would carry the weight of extraordinary evidence, thoroughly examined, but it would still encounter disbelief, alternative interpretations, and the full range of human responses to paradigm-shifting information. Some people would experience profound joy. The confirmation that we are not alone in the universe, that intelligence has arisen elsewhere, that the cosmic silence has finally broken, would be felt by many as a kind of liberation, a release from a loneliness that has been part of the human condition for as long as we have understood the scale of the cosmos. Some would feel uncertainty, even anxiety. The unknown nature of the civilization, its intentions, its level of advancement, its awareness of us would generate questions that no existing framework fully answers. The detection would open a door without revealing what lies beyond it. Others would feel humility, the realization that we are not unique, that the processes that gave rise to technological intelligence on Earth have done so elsewhere, would reframe the human story in ways that different people would experience very differently. And many would feel wonder, simple, profound, inarticulate wonder at the fact of it, that across 100 light-years of space, the light of another world had carried evidence of another mind. Consider the question that would immediately follow confirmation should we respond, and if so, how? This question, known in scientific circles as the question of active SETI, or messaging, extraterrestrial intelligence, is already debated without any confirmed target. The debate would become urgent and concrete with a confirmed detection. On one side, those who argue for sending a message point to the obvious. If we have detected them, they may have detected us. Earth's own radio transmissions have been radiating outward for over a century, and our atmospheric chemistry, the oxygen, the nitrogen dioxide, the traces of industrial activity has been readable by any sufficiently advanced telescope for decades. We may already have announced our presence, inadvertently, long before any deliberate message. On this view, the question is not whether to communicate, but whether to do so deliberately and thoughtfully, rather than leaving only the inadvertent signal of our existence. On the other side, those who counsel caution, among them the late Stephen Hawking, point to the historical record on Earth when technologically disparate civilizations have encountered each other. The encounter between European civilization and the indigenous peoples of the Americas, Australia, and Africa serves as a sobering template. The more technologically advanced civilization rarely proved gentle in the encounter, but these arguments from terrestrial history may not translate to interstellar contexts. A civilization capable of detecting Earth, or one that we have detected, is separated from us by at least 100 light-years. Any interaction is constrained by the speed of light. Military conflict, colonization, resource extraction, the motivations behind most historical examples of technological disparity are essentially meaningless across interstellar distances on any practical timescale. The debate would be profound, and it would be, for the first time, conducted in the context of a real target, not an abstraction, but a specific star, a specific world, a specific other. A-R. As we move into the more philosophical chapters of our journey tonight, let us sit with what a confirmed detection would mean, not for science or policy or strategy, but for the deepest questions of human identity and meaning. For most of recorded human history, our species has occupied a special place in its own self-understanding. Whether through religious frameworks that placed humanity at the center of creation, or through the implicit assumption of many secular worldviews that intelligence is Earth's unique achievement, we have, consciously or not, understood ourselves as singular, the universe as the backdrop for a human story, the stars as decoration for a stage on which we are the only actors. A confirmed detection would not merely add a second actor to that stage. It would dissolve the stage entirely and replace it with something much larger, much older, and much more complex. We would suddenly be one of at least two, and if two, then almost certainly many more. The galaxy, which had seemed an empty vastness, populated by indifferent stars, would reveal itself as something different, a place where minds have arisen in multiple locations, where the process that produced us has occurred again, elsewhere, independently. This would change the question of what we are fundamentally. Are we the universe's way of knowing itself, a unique phenomenon, the only example? Or are we one expression of a recurring cosmic process, one instance of something the universe does wherever conditions allow? Both possibilities are profound, but they are different kinds of profound, and a confirmed detection would answer, definitively, which kind we are. We are not unique. We are participants in something larger, members of a community we did not know existed. That is perhaps the most significant change in human self-understanding since Copernicus moved the Earth from the center of the solar system. Let us sit with something quieter and more personal, the loneliness that has, perhaps without our fully recognizing it, been a condition of human existence since we first understood the scale of the universe. Carl Sagan described it beautifully. Look again at that pale blue dot. That's here. That's home. That's us. On a mote of dust, suspended in a sunbeam. The Earth is a very small stage in a vast cosmic arena. The scale of the cosmos, 2 trillion galaxies, each containing hundreds of billions of stars, has always carried a particular quality of silence. Not the silence of an empty room, but the silence of a vastness in which we have been unable to find another voice. A silence that is not peaceful but searching. The silence of someone calling out and hearing no answer. That silence has shaped human culture in ways both conscious and unconscious. It is present in the existentialist philosophies of the 20th century. It is present in the particular quality of awe and melancholy that the night sky evokes. It is present in every generation of human beings who have looked up and wondered whether anyone, anywhere, is looking back. A confirmed detection would end that silence. Not with a conversation, not immediately, not in any ordinary sense, given the distances involved, but with the knowledge that the silence was not an answer. It was simply waiting. Another mind exists. Somewhere in the galaxy, matter organized itself into awareness. Stars and chemistry and time produce something that thinks, that builds, that leaves marks on the air of its world, that travel outward as light and reach, eventually, a telescope floating in space near a small blue planet. The universe is not empty of minds. That knowledge alone, that single fact, would change the quality of every night sky that human eyes have ever looked at, and every one they will look at after. As we continue our journey, let us consider the scientific program that would follow a confirmed detection, because the detection itself, extraordinary as it would be only the beginning of a sustained and profound scientific investigation. The immediate priority would be more observations, more transits, more accumulated photon counts, more precise spectral measurements. Astronomers would want to characterize the atmospheric chemistry of the planet in as much detail as current technology permits, not just confirming the technosignature molecules, but mapping their concentrations, their seasonal variations, if any, their altitude distribution. They would want to understand the planet's physical properties more precisely. Its size, refined through careful transit photometry. Its mass, if a radial velocity signal could be detected in the host star's spectrum. Its density, and from density, its likely bulk composition. Is it a rocky world with an iron core and silicate mantle, broadly similar to Earth? Or something different, a super-Earth with a thicker atmosphere, perhaps, or a world with a different geological history? They would want to understand the host star deeply, its age, which would tell us how long the civilization has had to develop. Its activity level, the frequency and intensity of stellar flares that might affect the planet's habitability. Its chemical composition, which would inform the raw materials available to the planet's chemistry and biology. And they would want to look for additional signals, not just atmospheric chemistry, but any other potentially informative observation. The planet's thermal emission, its reflected light spectrum, any variation in brightness that might suggest large-scale surface features. All of this would be the work of years, perhaps decades, a sustained, coordinated scientific effort, unprecedented in the history of astronomy. Every space-capable nation, every major observatory, every relevant instrument would be trained on the same star, the same planet, the same extraordinary fact. The question of another world, another mind, would become the central question of science. Let us consider the timescale on which understanding of such a detection would deepen, because it is a timescale that extends well beyond any individual lifetime. The light we detect from a planet 100 light-years away left that world 100 years ago. As Webb and its successors accumulate observations over decades, they will be building a time series of that ancient light watching, in extraordinary slow motion, how the atmospheric chemistry of the planet has evolved over the years of observation. If the civilization is active and changing, if its industrial output is growing, or shifting, or declining, those changes might be detectable over the span of a human lifetime of observation. The trend lines of atmospheric chemistry might tell a story about a civilization's trajectory. Over centuries, as telescopes improve and observation programs continue, the picture would deepen. Future generations of astronomers would have access to a century-long baseline of atmospheric chemistry data on this planet, a richer record than any single generation could assemble. And if, in the far future, space-based telescopes of much greater capability are developed telescopes with collecting areas orders of magnitude larger than Webb, capable of direct imaging of the planet, capable of resolving surface features, the character of the knowledge would shift entirely, from atmospheric chemistry to surface mapping, from inference to observation. The civilization on that world would gradually become knowable in ways that current technology cannot achieve. And meanwhile, the light leaving Earth today, carrying the signature of our own atmospheric chemistry, our own industrial activity, our own presence, would be arriving at that world in 100 years. If they are looking, they may already know we are here. They are waiting for us to answer. Whether we will, and how, is a question not for science alone, but for all of humanity. As we approach the final chapter of our journey tonight, let us step back to the widest possible perspective and hold the scenario we have been exploring in its full cosmic context. The observable universe contains approximately 2 trillion galaxies. Each galaxy contains, on average, hundreds of billions of stars. Around many of those stars orbit planets. The Milky Way alone, our home galaxy, contains perhaps hundreds of billions of worlds. Against that backdrop, a confirmed detection of a second technological civilization within 100 light-years of Earth is both an extraordinary discovery and, in a certain frame of reference, exactly what one might expect from a universe so vast, so old, and so richly structured. 2 candles in the dark, 2 small concentrations of matter that have, through the blind working of physics and chemistry and biology and time, organized themselves into something that thinks and builds and reaches outward into the cosmos, 100 light-years apart, separated by a distance that light crosses in a century. Connected, for the first time, by the faint signal of molecular absorption in a planetary spectrum. The universe is approximately 13.8 billion years old. The Milky Way is approximately 10 billion years old. Our sun has been burning for 4.5 billion years. The emergence of technological civilization on Earth has taken perhaps 4 billion years of biological evolution, followed by a few 100,000 years of human cultural development, followed by a few centuries of science and technology. That journey, 4 billion years to produce a species capable of looking across 100 light-years and reading the chemistry of another world, is either a typical journey or an extraordinary one. We do not yet know which, but a confirmed second detection would tell us. It would tell us that the journey can be made, that the universe permits it, that in the cold and dark between the stars, in the vast and mostly empty cosmic web, intelligence has found its way into existence more than once. 2 candles, in an ocean of dark, flickering with the same improbable light. And so we arrive, gently and without hurry, at the end of our journey tonight. We have traveled far together. From the elegant physics of transit spectroscopy, the way a telescope reads the chemistry of a distant atmosphere by watching starlight pass through it, to the concept of technosignatures and the molecules that only civilization produces. We have followed the careful, painstaking process by which science would verify such a detection, and we have sat with what the detection would and would not tell us. We have considered how the discovery would transform the Fermi paradox, dissolving its most fundamental premise. We have thought about the nature of the civilization, young, perhaps, industrial, perhaps not so different from us at a certain phase of our own development. We have contemplated how humanity would respond, what it would mean for our self-understanding, and what science would do in the decades and centuries that followed. And we have held the whole scenario in its proper cosmic context, two small concentrations of awareness in an immense and mostly dark universe, separated by 100 light years, connected by light. There is something I want to leave with you as we arrive at rest. The scenario we have explored tonight is not merely a thought experiment. It is the scenario that thousands of real scientists working at real observatories, writing real papers, submitting real proposals, pointing real telescopes at real stars are actively working to either confirm or rule out. The James Webb Space Telescope is observing exoplanet atmospheres right now. NDA. The data it returns is being analyzed for precisely these kinds of signatures, not with expectation of immediate discovery, but with the patient, rigorous attention that has always characterized science at its best. We are, for the first time in human history, in possession of instruments capable of detecting the atmospheric chemistry of worlds around other stars. We are, for the first time, in a position to answer the question empirically rather than philosophically. The answer may not come this year. It may not come in this decade. It may take generations of observation with improving technology before the signal, if it exists, becomes clear enough to trust. But the search is real, the method is sound, and the universe is under no obligation to be empty. Tonight, as you settle toward rest, carry with you the awareness of what is happening right now, in the cold darkness of space, 1.5 million kilometers from Earth. A telescope the size of a tennis court, its golden mirror segments aligned to nanometer precision, is pointing at a star, collecting photons that have traveled for decades or centuries to arrive at its detectors, spreading that ancient light into its component wavelengths and reading, with extraordinary patience and extraordinary precision, the chemistry of another world's air. Most of the time, it finds water vapor and carbon dioxide and the unremarkable signatures of a world without industry. Most of the time, the spectrum is interesting, but not extraordinary. But every night that it observes is a night when the answer could be different. Every new planet, every new transit, every new accumulation of photons is another chance for the universe to answer the question that humanity has been asking since we first understood how large the cosmos is. Are we alone? The universe is old, it is vast, it is full of stars and worlds and the raw materials of chemistry and biology. It has been producing complexity for nearly 14 billion years. And somewhere in it, perhaps close, perhaps far, perhaps in the direction of a star visible to you on a clear winter night, something else has been happening, something that thinks, something that builds, something that has, perhaps without knowing it, been leaving its signature on the light that travels outward from its world. That light is already on its way. Perhaps it has already arrived. Rest now, in the warmth of that possibility. Not as certainty. Science does not offer certainties here, not yet, but as genuine, honest, scientifically grounded wonder at the fact that the question can now be asked by instruments rather than merely by imagination. The universe has been silent for a long time, but telescopes, like questions, are patient, and the light always arrives eventually. Thank you for exploring with us tonight. May your rest be as deep as the dark between the stars and as full of quiet, undiscovered light.